this is your mode theory for a circular waveguide in optical fiber. So there are three different patterns being illustrated. One is the TE0. So what is this TE0 is that you can see the core is the inner of the optical fiber, the cladding is the outer. So this core will be having a refractive index of N1, cladding will have a refractive index N2. So these are being represented here. So in this I draw a reference axis. So this dotted is a reference axis. So in this, if the field pattern or the field of propagation of your optical fiber signal is in like this, okay, where the field of optical fiber will be concentrated more towards the center of the core or the axle of the core. So at the axle of the core, the field pattern will be moving with a higher intensity. So this type we call as TE0. So 0 indicates that it doesn't crosses the reference axis. You can see that the field pattern of TE0 in cladding is like this. It is having, it doesn't crosses in core, it doesn't crosses at all. You can see that it is going with an higher peak at the center, and at the edges it goes to a minimal value. It is the same in this side also. So 0 crossings is present. So we call this as TE0 mode. So whereas when we see another reference axis we take, and a TE1 we represent. So in this, the field pattern will cross at least once, okay, or it will cross only one time across the reference axis. So this is your reference axis, the dotted is your reference axis. The field of the optical wave or the light wave will propagate at the cladding in this fashion, and it will have a peaker at this point, and it will cross the reference in this point, and it will have like this pattern. Then it will move on to the cladding part. So here there is one crossing. You can see that at the center it crosses one time. So this mode we called as TE1 mode. Next is TE2. So in TE2, the crossings will be two times. You can see that with respect to the reference axis. So this is your reference axis. The optical signal which is being propagating along the core, along the cladding will be like this, and at the core it starts and it goes to the reference. You can see that it crosses the first time reference axis, then it creates electric field pattern, then again it crosses, again it comes back to the cladding as it is. So here two crossings occur, this point and this point. So we call this field pattern as TE2, and it goes on TE5, TE7, TE11, TE12, TE13, TE15, TE17. So that indicates that the number which is present in the subscript of TE is indicating the crossings of reference axis. Okay, and these three field patterns are having good propagation of optical signals in mode theory, whereas TE7 and the remaining which are not shown here, TE5, 7, 10, 11, 12, 13, 15 and 17 are all leaky modes, where they tend to have more crossings. Since there are more crossings, there are more losses in that. So that is what the leaky modes are. So leaky modes are those which partially confined to core region attenuate continuously, radiating their power out of core as they propagate, and which is mainly due to the tunneling effects. So this mode theory is confined by this equation. N2 is the refractive index of cladding, N1 is the refractive index of core. So in between this one is this beta will lay. So the propagation constant, as you had studied in electromagnetic fields, beta is the propagation constant. This beta will should be always in between N2K to N1K. If it is not in between, then the whole fiber will not transmit any optical waves. Uh, this is how your cylindrical waveguide. This is the mode theory for your circular waveguide, which uses cylindrical structures. So where it uses the Maxwell's equations. So I think you all are familiar with the Maxwell's equation. Equation 1, del cross E is equal to minus dou B by dou T. Del cross H is equal to dou D by dou T. Del dot D is equal to 0. Dot B is equal to 0 for a free charge region. So where D is epsilon E, B is equal to mu H. Epsilon is the permittivity and mu is the permeability of the medium. So you all are familiar with this Maxwell's equation. So here we are going to find with respect to the electromagnetic wave propagating along cylindrical waveguide. So the same concept is being utilized as well as in your optical fibers, assuming the field patterns are same. Okay, so this is your core fiber. You can see this is your core fiber. This is your core. This circle is a core fiber. This is your fiber axis with radius r, which is being deployed on a three coordinate systems x, y, z in cylindrical. So in cylindrical we have r, theta, and phi. So you can see that phi, the angle being created on x coordinate. So we can find the electric field as E is equal to E naught r comma phi e power j omega t minus bz. Z is the direction of propagation of the wave. So h is equal to h naught r comma phi e power j omega t minus beta z. So on simplifying by taking determinants, you can find the value of ER, E5, HR, H5. H, as we are done in cylindrical waveguide determination in unit number 3, no, unit number 4 in electromagnetic fields. So ER is equal to minus J divided by Q square, beta into dou Ez divided by dou R, plus mu omega divided by R dou XZ divided by dou phi. E5 is equal to minus J divided by Q square, beta by R dou Ez divided by dou phi minus mu omega dou XZ divided by dou R. HR is equal to minus J divided by Q square, beta into dou XZ divided by dou R minus omega epsilon by R dou Ez divided by dou phi. So H5 is equal to minus J divided by Q square, beta divided by R dou XZ divided by dou phi plus omega epsilon dou Ez divided by dou R. So for this, refer your electromagnetic fields subject unit number 4. Determination of all the 6 different parameters, electric fields and magnetic fields parameters for a plane wave equations. So this would be a harmonic wave functions. in terms of cylindrical. So for TE mode, for TE mode, the propagation will occur through the metallic waveguides. The Hz and Ez will be 0. In TE mode, Hz will be finite, Ez will be 0. So the electric field lies entirely in the transverse plane. The magnetic field vector will have a component in the direction of z as well as transverse. The propagation in z direction takes place with group velocity Vg. E and H plane moves at an angle normal to itself with the speed of velocity of light. So TM modes, we have Hz is equal to 0. The magnetic field along the direction of propagation H will be 0. Ez will be finite. So magnetic field lies entirely in transverse plane. Electric field vector will have component direction of z as well as transverse. The propagation in z direction takes place with group velocity Vg. EH plane moves at angle normal to itself with speed of light. So this is a hybrid mode. So the TE mode will have Ez is equal to 0, TM mode will have Z is equal to 0. When we combine it for TEM mode, Ez is equal to 0, Hz is equal to 0. So this occurs through free space, parallel wire or coaxial cables. Since ET and HT are perpendicular to each other and to the direction of propagation, the electromagnetic wave will propagate during superimposition of E plane and H plane together. Next mode is the hybrid mode where Hz is finite and Ez is finite. So here both the magnetic field and electric field vectors will have components in the direction of Z as well as transverse. So if ET is greater than HT, it is called as EH mode. If it is HT is greater than ET, it called as HE mode. I think all are familiar with the terms called ET and HTs. Tangential components of electric field. HT is the tangential component of magnetic field. Okay. We should keep a note that the meridional rays will take place only in TE and TM mode, which is completely guided. Q rays will propagate entirely in hybrid HE and EH mode, since they may contribute to the loss through leakage and radiation. So keep in remembrance, meridional rays will take place only in TE and TM, whereas Q rays will take place only in hybrid HE and EH. So this are out of fluoroscope. So any queries in this presentation? The mode theory of optical waveguides. Any queries? You can type in chat box. பாக்ஸ்ல இருக்கு. இப்படியே பாப்பா இது கிடையாது. Okay, since I couldn't find any queries in chat box, no queries, I move on to the next presentation, okay, which is evolution of optical fibers. How these optical fibers came into existence, how they are being treated now, how it will be treated in future, what are its different generations. Okay, so this graph will give us an idea of how the optical fibers came into evolution. So the optical fibers were first used for long distance communications at railway stations. Most Morse was the inventor of this optical light communication system. Before Morse, there were railway stations being present in order to safeguard the moving of passengers, moving of goods, materials in a safer way. And during the moments of all these things, what will happen is that there was threat of thefts, threat of mishandling and robbery of all these goods. And the arrival of uh, trains at railway stations was unknown during early 1700s, 1750s, and so on. So what they did is that they used lamps at higher altitudes or nearby mountains, or they used lamps, different types of lamps, colorings, to indicate the movement of uh, the train coming at which distance. So that was the first optical communication which was evolved by man. Usage of lights, lamps, not lines, lamps at nearby higher areas or hills or mountains to indicate the presence or the movement of railways to the station master or to the people or to the passengers. who want to board the train. So with that, the evolution of optical communication started, and during uh, the 19th century, the optical communication started its communication with a good performance by the evolution of integrated chips. The integrated chips was the first basic fundamental, so where the movement from usage from transistors to ICs were being developed. So in that case, the first generation started during the year 1975, which used first Windows system with a capacity of 10 power 1 gigabits per kilometer. Then during 1983, the second generation was evolved using second window, which had a capacity of 10 power 2 gigabits per second per kilometer. And during 1988, the third generation was being developed, which used a third window, and the data rate was, or the capacity of handling was around 10 power 3 gigabits per second per kilometer, for every kilometers. Then after that, the evolution started to double itself for every year. So every year there was an increase in the data rate, and till 2000 it was the fourth generation being dominated, which had increased the data rate to 10 power 6 gigabits per second per kilometer. So this is the generation of the optical fibers. So now this has come to 5 generations. In term, this has come to 5 generation according to the University of Rochester. University of Rochester is saying the optical communication has come to fifth generations. The Institute of Optics at University of Rochester is giving this data. Okay. So in the year 1980, the wavelength which was used in first generation was the 0.8 micrometer systems. The same diagram here. Same diagram is shown here. And the type of fibers which was used is your graded index fibers, GI fibers. In 1985, second window started, where the operating wavelength was at 1.3 micrometer, used with single mode fibers. In 1990, the third window systems were being evolved by using single mode lasers operating at 1.55 micrometer systems. Then in 1996, it was further developed to WDM systems, wavelength division multiplexing systems, by using optical amplifiers. Then it was further developed into the fifth generation by using the Raman amplification by using L and S bands during the year 2002. So these are the 5 generations of optical fibers. So this is the first window, second window, third window, depending on the wavelength. So this x-axis is the wavelength, range from 600 nanometer, 800, 1000, 1200, 1400, 1600, 1800 nanometer. So this is your first window, this is the second window, this is the third window. And this represents the year of evolution. So the red color represents the years of evolution. So this was the window being used till the 1970s. So this window, which had an attenuation of about 10 decibels for every kilometer. So see here, this rectile line. Any variations? Yes. And the operating wavelength was around 850 nanometers. Then during the second generations, this is a second window which operates at 1330 nanometers. Okay. Here the first window operated at 850 nanometer, the second window operated at 1330 nanometer, so which had a reduced in attenuation. You can see that the attenuation level was reduced to 3 decibels. You can see that 3 decibels. And in the third window, which is used at 1550 nanometer, giving nearly 1.5 decibels of attenuation per kilometer only. Okay. So here they are used the dope diffused silica optical fibers, which is showing a dispersion at 1.3. You can see that here. This is a dispersion. The second generation optical fiber came with the field of indium gallium arsenide diode laser as a transmitter, which we had discussed earlier. The third generation fiber optic systems operated at 1555 micrometer and having a loss of about 0.2 decibels. Was achieved by indium gallium arsenide phosphide semiconductor. So along with this advent, DPN invented the EDFAs, erbium doped fiber amplifiers, that we will be studying in unit number 5. Okay, which are being used as repeaters in long distance communications. PN invented the EDFAs, erbium doped fiber amplifiers. So any queries in this presentation, you can type in chat box.